Hello, everyone. My name is Prasanjit Singh, and today I'll discuss with you software architectural patterns. So, we will be essentially focusing on what software architecture pattern is and why it is needed for software developers and solutions architect to learn or know about these patterns. How do they help to develop your architecture for your infrastructure stack that you're building, possibly on the cloud, and to understand or weigh in whether what kind of design pattern is good. So we'll be mostly focusing on efficient software design patterns, and uh, and then I'll introduce to you different architectural design patterns and their advantages, disadvantages, and so on. So we'll explore each of these patterns and try to understand. So this will allow you to think as a solutions architect whenever you're approaching any problem. So you have to think and work like an architect so that your thinking or reflects on your work that you do. It's not that we have a business problem and we just translate into technical language. We have to think through it so that this particular project that we deliver becomes scalable and holds good even when the traffic grows, the demand grows, and so on. Like when you build something, it should be robust, highly available, and there are many such paradigms that have to be done correctly so that everything works perfectly fine and it is called as a good architecture. So what is a software architecture pattern? Before delving into common architectural patterns, let's take a step back and understand what software architecture is all about. So let me simply explain you this. Software architecture is nothing but you can imagine it as a pictorial representation of the IT system that communicates, organization of the system, how it is composed, different components and their functions, and then finally how they interact with each other. That's all a software architecture is all about. Like it's about a pictorial representation of your architecture or your infrastructure, your logical representation of your software, and the various components that make this particular architectural system, their functions and their interactions. So that is all about software architecture. And this schematic representation is nothing but an outcome of a design. Like every architectural representation or diagram or drawing, whatever you are seeing, behind it is a design. So whatever has been done is based on that design. So this design pattern is what we are going to focus today. So these design patterns also follow some principles, and these principles drive the decisions that solution architects make. So a typical software architecture requires decisions regarding, say, performance, security, manageability, scalability, and so on. So why should you focus on software architecture? Like what happens if we just build our things right away without thinking of any design pattern behind it? Uh, well, that leads to disasters. Like if it is not well thought out, it might fail. So design principles, architectural decisions, and their outcome, that is software architecture together, enable a software system to deliver the business operational and technical objectives, as I said, and that allows you to build good software system. A software development team makes the first set of decisions regarding the software architecture pattern selection, that is in normal cases, and the business requirements that are available at that stage are used to drive these decisions. So the first set of decisions are crucial in any project because suboptimal decision making can lead to more budget or a bad architectural design. Now, sometimes software or solutions architects, what they do is make models, and based on that model, they build the original thing. So that is another thing. I'll come to it in a while. Now, how do you know if your software architecture is good? So you have to know certain pointers that allows you to understand whether the architecture that you did is a good software architecture. So one is, it should be easy to maintain. The business stakeholders should be able to understand that architecture easily, because you are building a technical thing, but it should be easily translatable to non-technical people as well. Only then you know that this is a good architecture, because even a layman can make sense out of it. And then good software architectures are usable over the long term. They are reliable, and they are stable. And finally, this architecture should be able to scale. Like when your traffic grows, when the adoption of that particular software grows, it should not be the end of that particular design. Like it should allow growth, because everything that is designed will grow with time, and the architecture should be designed keeping that in mind. And finally, at a code level, it should be ensured that there is no repetition of code, that the code is written in a way that it is easily understandable and can be refactored over time with change in requirements. Well, that's a long introduction. Now let's get into understanding what software architecture patterns are, what are the different kind of software architecture design patterns, and what are the pros and cons, when do you use what, and so on. So the first architectural pattern that we'll discuss is this one: layered architecture. Now, we often use the N-tier architecture. When we talk about architecture, you might have heard about three-tier model or two-tier model and so on. So what is this? This is called a layered pattern architecture. And now it is one of the most commonly used patterns where the code is arranged in layers. And the key characteristics of this layered pattern is the outmost layer that you see is where the data will enter the system, and the data passes through the subsequent layers and reaches the innermost layer, which is the database layer. So you will see the data enters from a layer which is not the database and eventually reaches the database. Simple implementations of this pattern have at least three layers: the presentation layer, the application layer, and the data layer. The users access the presentation layer, maybe using a GUI, and the application layer runs the logic, it has the business rules, and then the data layer is the source of truth, or has the database for storage and retrieval of the data. This pattern has lots of advantages, and that is why it is the most commonly heard pattern. And one of them is maintaining these kind of software is easy, because each of the tiers are segregated. So one can easily make changes without affecting the other layers. Development teams find it easy to manage this kind of a software infrastructure, and it allows you to develop large-scale web and cloud-hosted applications. Now, Java Enterprise uses this pattern, and if you have worked on applications using Java Spring Boot and so on, so it uses this particular pattern, layered architecture pattern. Now, there are some disadvantages as well. The code can become too large, and a considerable part of the code only passes data between layers instead of executing any business logic. And this can cause a performance issue as the adoption of this particular software stack grows. With growth in traffic, it can adversely impact performance. Well, that is one. Next is the client-server architecture. Now, the client-server architecture pattern is also very common. Here you have two entities, the client and the server, and the following like the key characteristics that follow a client-server architecture are: the client component sends a request to the server, which then processes them and then responds back. And when a server accepts the request from the client, then it opens a connection, And to open up a connection, it uses a specific protocol and talks like the client server communicate to each other. They talk to each other using that specific protocol. And the servers in this case can be stateful or stateless. Let me tell you what they are. Like a stateful server can receive multiple requests from the clients and maintain a record of requests from the client. And when that happens, and when the client server requests are recorded, then that is called a session. So this kind of communication is a stateful application, while in case of stateless, the client calls the server, there's no session built, and the server executes the request. That's all. So there is no record of whether there was session established between the two. So there are advantages to stateless as well. We'll come to that in a while again. So email applications are good examples of client-server patterns. Now, client accesses data from the server using authorized access, which improves sharing of the data. So that is a very good advantage of this client-server system. Accessing the service via user interface is done, so there is no need to run terminal sessions or command prompts. Client server applications can be built irrespective of the platform or technology stack. And finally, another good thing about client server design pattern is that it is a distributed model, and specific client server pairs can be done for specific responsibilities. So it is highly scalable. Now, there are some disadvantages as well. Like if there is a lot of load on a particular server from the client end, then the server can slow down, but that has solutions, but can be considered as one disadvantage. And then a central server is mostly needed to support multiple clients. So that often becomes a single point of failure. So these could be some, so to say, disadvantages of the client server model. Now, the next design pattern is the master slave. This one is also very famous. You might have heard about MySQL, master slave servers, replicas, and so on. So master slave architecture pattern is useful when the clients make multiple instances on the same request, and the request needs simultaneous handling. The key characteristics of master-slave architectural pattern is that the master launches slaves when it receives simultaneous requests. The slaves work in parallel, and the operation is complete only when all the slaves complete processing the respective requests. Advantages to this pattern are that applications read from slaves without any impact on the master, and taking a slave online and bringing it back offline is also okay, because you can do synchronization at any time the slave connects to the master. So which is a good thing. Like you would not have downtime if you have multiple slaves and one of them goes down, and you can bring it back and sync it up and bring it all online. Now, there are some disadvantages as well. Sometimes these kind of patterns do not have automatic failover. And yeah, the writing is possible on the master only. So if the master fails, slaves are no good. They just become read only, and you have to intervene and promote the slave to be a master and then continue with operations. And failure of a master typically would require some amount of downtime in that case. Well, that is about the master slave. Now comes our next pattern that we call the pipe filter pattern. This is not very, very common. So some of you might not have heard about the pipe filter pattern. Now, if you look at this image, just imagine you have a complex processing in hand. You would like to break it down into separate tasks and process them separately. Now, this is where a pipe filter pattern comes in. Now, what are the characteristics of a pipe filter pattern? One is the code for each task is relatively small, and you treat it as one independent filter. You can deploy, maintain, scale, and reuse code in each filter. And finally, the stream of data that each filter processes passes through pipe. These are the features of a pipe filter model. Now, you might be wondering, where is this used? Now, compilers which compile our code use this pattern due to advantages like they allow repetitive steps such as reading the source code, parsing, generating code, etc. These can be organized as separate filters, and each filter can perform its processing in parallel if the data input is arranged as streams using pipes. And this model is very resilient since the pipeline can reschedule the work and assign it to another instance of that filter. So that is where the pipe filter model comes handy. But disadvantages are like this model is a bit complex, and data loss between filters is possible in case of failures unless a very, very reliable infrastructure is used. So this is normally used mostly internally with language compilers. Now, there is another architectural pattern that is common. It's called a broker pattern. Now consider a distributed system with components that provide different services independent of each other. Now, independent components can be heterogeneous systems on different servers. However, clients need their requests serviced, so a broker architecture pattern is a solution to this. Now, what are the characteristics of a broker architecture? If you're looking at the diagram, you'll understand that broker component coordinates the requests and responses between the clients and servers. So we went through the client server architecture a while ago. So that is where the client directly talks to the servers. Now broker acts as a middleware here, and it coordinates the requests and responses. The broker has the details of the servers and the individual services they provide. The main components of the broker architecture patterns are client servers and brokers. It also has bridges and proxies, which it can use to route its request, and when it gets the responses, it can send the response back to the client. Now, these are the good things about this architecture. So this middleman, the broker, takes care of the requests and responses between the client and server. So that allows more flexibility. The broker not being available might cause issues because the client and servers do not have any way to communicate with each other without the broker. So these are the issues with this architecture, but it is very popular and successful. Now, you might have heard about another design pattern that is called peer-to-peer or P2P design pattern. Most of you might have used this when downloading things from torrent. So torrent networks are P2P networks. So what happens in this design pattern? The peer-to-peer pattern is strikingly different from the client-server pattern, since each computer on the network has the same authority. Like in peer-to-peer, you don't have a server which is like the master or having every thing that is being processed is being on that node, and there is a client that is a smaller node that just requests and gets back its responses. So, but in a peer-to-peer, like each computer on that peer-to-peer network is equally competent and has equal capabilities. Now, each computer can function as a client or a server. So it's flexible there. When more computers join the network, the overall capacity of that network increases in case of P2P. Another example apart from torrent could be Bitcoin or cryptocurrency networks. So these also use P2P, and P2P networks are decentralized and therefore they are more secure. You must have already heard about Bitcoin networks lately, and they use P2P, and they're very secure as well, and hackers cannot just compromise everything by hacking into one server in that network, because every node could be a server here. Well, the next pattern is the event bus pattern. So what is the event bus pattern? If you look at this diagram, there are applications where components act only when there is data to be processed. At other times, these components are inactive. Event bus pattern works well for these and has the characteristics like it has a central agent, which is an event bus, accepts the input. Different components handle different functions, and therefore event bus routes the data to the appropriate module. The modules that don't receive any data pertaining to the functions will remain inactive. And to explain this, let me give you an example. Now think of a website using JavaScript. The user's mouse clicks and the keystrokes are nothing but data inputs. So the event bus will collate these inputs and it will send the data to appropriate modules. Now, this allows for a lot of advantages. Number one, this kind of a pattern helps developers handle complexity. Now, one more possible advantage is it is very scalable, and it is an extensible architecture where new functionalities will only require a new type of events to be put in. Now, this kind of an architectural pattern is used a lot with Android development. There are some disadvantages with this pattern as well. Testing of interdependent components becomes an elaborate process with this kind of a design pattern. And if different components handle the same event, they require complex treatment to error handling. Some amount of messaging overhead is also typical when we are using this pattern. So when this pattern is used, the development team should always think of sufficient fallback options, because event buses can fail and one has to handle those failures with retries or some other mechanisms. Well, now comes another pattern that is called the MVC. This is also a very popular design pattern, the Model View Controller or MVC model. Now, the MVC architectural pattern involves separating the application's data model, presentation, and control aspects. So this leads to characteristics like there are three building blocks: model, view, and controller. Application data resides in the model. The users see the application data through the view. However, the view cannot influence what the user will do with the data. And finally, the controller is the building block between the model and the view. The view triggers events. Subsequently, the controller acts on it, and the action is typically method call to the model. The response is then shown in the view. Hope you got a hang of it. So basically, to wrap it up, the controller is the building block between the model and the view. The view triggers events. Subsequently, the controller acts on it, and the action typically is a method call that happens to the model, and the response is shown back in the view. So that is what it is. It is popular, and many web frameworks like Spring, Java Spring, Ruby Rails use it, and even a lot of PHP-based frameworks like YII use it, and using this model expedites development teams can present multiple views to the users, and the changes to the UI is common in web applications. However, MVC pattern doesn't need changes, and the model doesn't format data before presenting to the users. Therefore, you can use this pattern with any kind of a graphical interface. So very popular and very relevant for application development. And there are some disadvantages as well to this MVC pattern. With this pattern, the code has new layers, and it makes it harder to navigate the code. And there is typically a learning curve for this pattern. You have to learn about the MVC frameworks before you can aggressively start developing in an MVC architecture. So there is kind of a learning curve for this. Now, we move on to the next software architecture pattern, Now, this design pattern is called the Blackboard pattern. Now, this pattern emerges from AI development or artificial intelligence development. The Blackboard architecture pattern is more of a stopgap arrangements. Its characteristics are like when you deal with an emerging domain like machine learning or AI, you don't necessarily have a settled architecture pattern to use. So you start using the Blackboard pattern. Subsequently, when the domain matures, you adopt a different architecture pattern. So this can be called as a stopgap pattern. So basically, there are three components here again: the Blackboard, the collection of knowledge resources, and the controller. So the application system stores the relevant information in the Blackboard, and the knowledge resources could be algorithms that AI or ML contexts use. And these algorithms collect the information and updates in the Blackboard, and then the controller reads from the Blackboard and updates the application assets with the learnings. So image recognition, speech recognition, all of them use the Blackboard architecture pattern. It has advantages. The pattern facilitates experiment. You can reuse knowledge resources like these algorithms. You can reuse the trained models that you have. And the disadvantages with this model are ultimately you will need to have a stable architecture pattern that will evolve after you move out of the Blackboard pattern. So it is just a stopgap arrangement, not a permanent framework. And testing can be difficult in this kind of an environment because there is no fixed architectural pattern in case of a Blackboard pattern, no fixed algorithm and so on. Well, that is all to the Blackboard pattern. Next, we move on to the design pattern that we call the interpreter pattern. A pattern specific to certain use cases. This interpreter pattern deals with the grammar of programming languages. Very, very specific use case. That's why most of us haven't even heard about this. But the interpreter pattern offers an interpreter for the language. So how does it work? First is you interpret interface that aids in interpreting given context in a programming language. The pattern uses a hierarchy of expressions. It uses a tree structure that contains this expression. A parser external to the pattern generates the tree structure for evaluating the expressions. The use of this pattern is in creating classes from symbols in programming, and you create grammar for the language so that the interpretation of sentences becomes possible. Now, network protocol languages and SQL use this pattern. So that is all about different software design patterns that I wanted to discuss with you. We can delve deep in each of these with more examples. Please put in your feedback in the comments so that I'll try to work out on the design patterns that you would like to listen more from me. Thanks for joining in. Have a good day.